Yeah, everyone else will just have to catch up. Right, okay, so where were we last time? We were talking about heap data structures. And we had this picture of a binary tree. And remember, this was an almost complete binary tree because every node here has two children, except for these ones on the right here, and these ones could have 1 or 0 children. And if you remember, we'll also need to remember that what these numbers are about. So these are the addresses of the nodes in the tree. So you can traverse this tree sort of taking one of these addresses, 1011. So just ignoring the first one, or don't worry about just don't worry about the first one, but all the rest of them are kind of a left-right address system for where things are in this tree. And that first one is kind of useful because it gives you indices into an array if you're implementing it that way, but we're not. So yeah, if you look at this one, we're going left. It's a 0, then we're going right. There's a 1, and then we're going right again. That's a 1. So yeah, any one of these nodes can be reached. We've given its address. And what we're actually going to use that for is finding the position of the next sort of item in the tree here. So there's a node missing here, which would be the next one that you would add if you wanted to keep this as an almost complete binary tree. And that's the reason we also keep the size of the tree in the data structure. So yeah, last time I sort of said, oh, that's an optimization. Well, it's a pretty big optimization because you'd rather not have to search the whole tree just to find out where you're going to insert the next node. So yeah, it's not just for finding the size, it's also for finding where to insert and remove things from. Okay, yeah, last time I think we just got down to sort of some code to display a tree that was like this. But we want to do some more useful things. So I'm just going to run this code again so that I can continue to play with it. We need this one. And sorry, we don't need much from here, but we do need a few things. So we'll just run these ones. Let's get back to where we were at the end of last lecture. Okay, so I think we didn't get to push and pop. So, or did we get to these? No, I'm pretty sure I just constructed those trees by hand last time. I added the left and right children by hand. Now, what we've got here is we've got some 2 functions which are able to either add or remove this last node in the tree. So if you push will add a node to here, and pop will remove this node here. And if you don't know, those are just pretty standard weird names that people give to things in computer science, especially for stacks where you have just a list that you're always removing an n and adding to on the end. So if they sound like strange names, well, they kind of are a bit strange, but they're just the standard ones that everybody uses. So yeah, push means add something to a thing, basically, in Julia. And pop means remove an element with a key, a certain key. So yeah, strange names. Computer science is full of strange names like that. But I mean, so is mathematics, so it's okay. Okay, so what we need to do here is we're going to implement this function push, or I'll just walk you through how it works. This one's trying to add a node to that blank space to continue, make sure that its properties remains, well, that its structure remains to be like a almost complete binary tree. Okay, so one thing first that we're doing, does anybody know what this thing does? Have we seen this before? I'm not sure if we have. Yeah. Yeah, exactly. Yeah, so because main includes all the functions from base, we will have access to push normally. So we haven't done this code yet. So if I just show over here in this REPL, so I could push something onto an array like this. So I already have access to push, but as like something I can call, but if I want to overload it, I actually need to do an import like this. Or in fact, I would actually suggest don't do this in general. I would just write base.push. Generally speaking, that's probably a bit clearer, I would say, when you're overloading something, because it's just like, it's a relatively unusual thing to actually overload something as opposed to use it. And it's nice to know that you're actually doing that. So that's like what my suggestion would be. And we'll see further down, like in the modular example of this code, that that's actually what's being done. So anyway, okay, so that's the first bit. Right, so how does this actually work? So there's like this trivial case when the tree's empty, you just add the root node. The new node is the root node, so that's not very interesting. Otherwise, what we're going to do is find the address of the next node. Now that address is just the length of the tree. So that's pretty convenient, or the number of nodes in the tree. So we're just adding 1 to the number of nodes, and then that new number will be the address of this new node. Now remember that includes like a leading 1, which we don't care about in binary, but for the address, but the rest of it is going to tell us how to traverse the tree to find the place we're going to add that node. Okay, and we're trying, this is the, okay, so we haven't made the node yet, but this is the value that we want to add. So if you remember as well, this tree has been specialized for only strings as values, but we will generalize that in the next example further down. Okay, so how this works, what it does is it constructs this mask thing, which is going to pick out one of the bits in this bit representation or the binary representation. And so like, actually, maybe we'll just play with that. So if we had, okay, maybe I'll go through the code a little bit first, and we'll get this again. I've lost my place. Okay. There we are. Okay, so what we do is we have this loop, and all we're going to do is inspect the number, which is our address, and we'll mask it off with this mask. So that finds the sort of like bit we're interested in. And if it's not 0, then that means we need to go to the right subtree. So we're looking at the R child. Oh, sorry. Yeah, I could say in general, we're looking at the right child here. So we're just setting the current node to the right child. And then if the mask was 0, then we want to go left. So we're looking at the left child. And then at some point, we're going to reach the end of this bit representation, and we will have actually found where we're trying to add the thing. So that's what these other sections are about. So yeah, if the mask is 1, that's like the end of the bit representation, and we're going to add the new node to this right child here. And we'll also set the parent link. I'm not even sure this code uses the parent links, to be honest. I think it might use it further down, but it's maybe not in a particularly like inherent kind of way. So in this particular tree representation, I think we could omit the parent links, and it would actually make this thing a little bit simpler to like manipulate. But anyway, it doesn't matter. I guess the same thing on the other side. If we found that we needed to add it to the left, then we just set the L child to this new node. Okay, and so that's all there is to that. So let's, one thing I wanted to like point out is how the mask interacts with this. So this doesn't actually work that well, me expanding and making this smaller. Let's try it this way. So if we had the mask as a binary representation, so if we start out with the mask being something like that. So it's just a bit somewhere which is set. It will show it to us in yeah, it'll show it to us as an integer, a base 10 integer, but yeah. So what all we do every time we go through the loop is this operator here. So this means shift the mask left by one bit, and then we, I think I had some code that I sort of tried this out before with, whatever. So let's print the representation of the mask. So if you want to show something in binary, you can do something like this. Base equals 2. hopefully that actually works. So every time I've got it the wrong way around. Okay, so we actually want to be shifting it right, not left. But anyway, so basically every time through this loop, we're just shifting the bit representation to the right, and then yeah, then this AND operator is a bitwise operator. So then that picks out one particular bit of this number, and that's our address. Well, that's the component of our address we want to be looking left or right in the tree for. Okay, so that's all a little bit low level. And to be honest, like those low level bit operations are probably a bit unnecessary in this code because mostly what we're doing is following pointers around, and CPUs hate that. So if you want it to be fast, you should put all this stuff in an array like datastructures.jl does. But sometimes like you are stuck, you have to use a linked data structure. And so that's fine. When you're in that situation, then it's a good idea. Okay, so any questions about how push works? Nope. Okay. Right, so we want to also do the opposite of that, which is pop. And so in that case, we kind of want to do a very similar thing. I'm not sure it's even worth like going through all of this in detail. But one thing to note is that when we're popping this tree, when we're popping a value out of this tree, we are looking to take the root off. And the reason we do that is because later on when we have a heap, like a heap property for this tree. So this, by the way, I should emphasize that like this push here, this does nothing to do with heaps. There's no ordering in this tree. It's just putting something in there and making sure that it satisfies this the almost complete binary tree property. And the same thing for pop. This is going to remove the root node, and then it's going to get the node from like the end of the tree and put it where the root was. So it just swaps those basically. And it doesn't preserve any heap properties. There's no ordering. Because it really does basically the same thing. We get this mask and we look at the address, which is this num thing. We again look at the address, and eventually we decrement the number of nodes in the tree down here. And yeah, the rest of it is pretty much the same. We traverse the tree, we find the thing that we want to remove, and then we're just replacing the root with this new node that we found, and we just set the parent and child pointers, I guess, or references in Julia to like the appropriate things. So we can replace the root of the tree, and that's pretty much it. So yeah, that's pretty straightforward, I think. So with those ones, we can actually construct a tree. Now, did I put this code in the REPL or not? Not sure if I did. Shove that in there. Okay, so we could make this one here. So we could just paste in that. So, whoa, what is that about? I might just ignore that. I don't know what that's about. Okay, anyway, seems to have worked regardless. Let's just move right on from that error. Okay, so yeah, you can see that the tree, so what we've done is we've added okay, this is important. We've kind of added these strings, but they're in the order. We added them 1 to 9. And you can see that the first, like we've got 1, and then the left child is 2, the right child of that is 3. Then you can kind of see the way that it up the tree. It's this breadth first thing where it fills up the shallower layers of the tree first, and eventually you get down to the end. Okay, cool. So that's that. Okay, and we could remove an element. So let's pop an element off the tree. And we'll see that this removes the root. So we've removed the root, which is 1 from this tree. But if we look at the tree again, then we can see that the 9, which was previously in this kind of end position in the tree, which is the deepest rightmost node, has gone into this position. Okay. Now, if this was like an array-based implementation of this, then this would be as simple as swapping 2 elements of the array. And you can also compute the exact, like the address gives you the index of the array. So this is order 1. It's the fastest thing you could imagine, pretty much. But yeah, we don't have that in this code. Okay, so yeah, this doesn't have the heap property. So what's the heap property? Well, basically what we're wanting to do is remove, well, in our simulations, we want to remove the minimum time for the next event. In this code, we've actually implementing a max heap. So we're trying to remove the maximum thing from this tree. So the heap property would be that that every node is greater, or the value that is in that node is greater than the values that are in its children. And if we have that property, then we can know that we can remove the root and we'll get the thing that's the greatest. Or like for our simulation example, we can use less than either. It doesn't matter either way. You just need a nice ordering function to do the ordering. Okay, yeah, and there's a note here that, yeah, so that removing something is order 1, because all you need to, what was that? I mean, just having second thoughts about that, because I don't think that's actually true. I think it's order log n. I think that might be a mistake. So you do need to maintain the heap properties. So like we'll see the code that does that in a minute, but yeah, it's a log n time to insert and remove, I think. Does that sound right? We'll see it in a minute anyway. Okay, so let's make a max heap structure. So this is just going to have a tree inside of it. But in addition to that being a balanced binary tree, we're also going to maintain the heap property when we add things and remove things, when we make push and pop work for this. So we'll run that. And then we'll just have this show function. And note that like show node is being reused from the code we had further up. So all we need to do is just sort of have some bit of metadata here to say this is actually a heap. Print it out. Okay, so as part of pushing and popping from this heap, we need to implement 2 functions called sift up and sift down. That's just kind of conventional name for those. But basically what they do is they maintain this partial order of the tree. They add to the tree as a almost complete binary tree, and then they shuffle some nodes around to make sure, or some values to make sure that the heap property is preserved. Okay, so sift up, this is the easier one. So when we push something, so we add something onto the end of this tree, we're going to want to call sift up for the node that was added. And that will swap things around. So what we do is we look at the node, and if the parent is not nothing, so this is where we use the parent link. If the parent isn't, yeah, and actually this is it. This is actually required in this case. Like if you didn't have the parent, you would have to traverse it some other way and it would be less convenient. So yeah, this is required in this particular case. So yeah, sift up, what it does is if you have a parent and then we just compare the value of the parents, the value held in the parent and the value held in the current node. And if the sort of the like ordering property is violated, so remember we want the node in, because it's a max heap, we want the children to have values less than the parent. So yeah, if this isn't true, then we need to just basically swap the values in the parent and this current node. And then we just call sift up on the parent. So what we're going to do is we just traverse this from the leaf all the way down to the root. And if at any point we notice that the heap property is now satisfied, then we can stop basically. And also this is recursive. So this calls itself if necessary. And yeah, as I said earlier, I think in another lecture, that's like really typical. If you have a linked data structure like this and it's a graph, you kind of walk around it using recursive code. Pretty typical and like nice to write. Okay, so this is how we use it for push. Actually, I might just run that code as well. I hope I will do something with all this code I'm running. So yeah, for push, we just we add to the tree, the binary tree, and then we call sift up. And we also need this function last node, which we will see here. We don't really need to kind of talk about this in detail. This is exactly the same algorithms we've already seen before to find the last node in the tree. So you're just following the address left or right down the tree until you find the last node. Yeah, it's the same algorithm, just selecting the right bits of the address. And yeah, then we have push. Okay, so for the other case, if we pop an element, what we're going to do is remove the root, right? Because that's the one we want. That's the one that's the least or the greatest, depending. In this case, the greatest. And this requires this function called sift down. So this kind of does the opposite of sift up, but yeah, kind of. So, so actually, let's see it in the context of pop. So we'll do that first. So for pop, we like take the root. So that's what that does based on the pop of the tree. And then if the root if there's still a root left in the tree after that, then that will have been the value from like the end of the tree. So that's not in the relevant position. It's just in the root now, and that doesn't make sense. So what we're going to do is call sift down to move that node from the root, or the value of that node from the root to somewhere else. And this is how it works. So if there's only a left child of the current node, then we know oh, I should also say that this is sift down is recursive as well. So this is like we're calling it to start with on the root, but at some point we're going to reach the leaves potentially. And in that case, we need to, yeah, we might end up in this situation where there's only a left child, but there is no right child. In which case, we just look at the values and see whether they need to exchange them. Okay, so but this is the general case. So we can basically stop, and we know we have the heap property correct if like the value of the node is greater than the value in the children. So I mean, yeah, for the times again, we'd be using less than here, but that's okay. Yes, slightly confusing, sorry. Yeah, so if the node value is greater than the child values, then we're kind of done and we can just return. Otherwise, it's great. It could be great. It could be less than one of the values, but it is at least greater than one of the values. So we could just choose the one which is largest, and we'll like keep bubbling the value up into that part of the tree. So down into it. Okay, so that's like that why we choose the left or right. Yeah, so basically we just do the same thing. Like we just decide if we need to swap something, and we swap the values if we need to. Okay, cool. So we'll run that one. And I hope we will use this code in a minute. I think we'll run some examples. Okay. Okay, was there anything else to say here? Oh, okay, yeah, and it says here, in contrast to what it said further up, that push and pop are both order log n. Because we've got to traverse the tree potentially all the way from the root to the leaves, or vice versa. So that distance is log n, order log n. Okay. So can anyone tell me Like, is it evident why this even, like, does this preserve the properties that we need? Like, does it leave this as a complete binary tree, almost complete binary tree, for instance? And why? Any thoughts? Everyone's looking blank here. Okay, so you might have noticed that all we're doing is swapping values here. So this little bit of code here, it's just swapping values. So when we do sift down and sift up, all we're doing is swapping values from parents to children. So we're not changing the structure of the tree at all. So that's the reason that our almost complete binary tree remains an almost complete binary tree, because we don't change the structure. So the only functions that actually change the structure at all are this push and pop. And we know from construction of those ones that we use the address to traverse to the next position. So we know that those preserve the structure of our tree correctly. Okay. So yeah, all this code here needs to do is maintain the heap property. It doesn't need to maintain the structure of the tree. Okay. Right, so hopefully I ran all of that code in the right order and everything, and we can try adding some fancy people, I suppose, to this heap. The names of some people. So, we add all of those. Now we've got a heap which looks like this. And we should have found that the maximum string in this whole lot, which is promising. I mean, W is pretty towards the end of the alphabet, is in the root, and everything else, the like left and right children here, should be less than, in this case, less than the root here, which is in fact the case, which is good. So if we were to remove something, we should get the root value, which is goff with them, and the heap structure should have been preserved. So one of these two, is that true? One of these two should have ended up in the root position. And that's the case. And then anything like further down the tree, but only log n things, would have had to be rearranged. Okay. Oh yeah, we could remove all of them. And in fact, that would give us a list of everything in order. So we could do that. There you go. That's the remaining ones in order. And now at the end, our heap is empty. Right, and so just in this example code, we've got strings here, and we've also got a max heap, but but yeah, we can have the opposite. We can have arbitrary values in there as well, and we actually want floats in there. Or in fact, we want a pair of a float and an event in our actual case. But the thing that's going to do the ordering is the float. So if you remember, we had that timed event data structure. And we implemented base.less, I think, for that. So that defines the order. Right. Okay, so I think that's all there is to do with heaps. Is there any questions on that lot? No? Okay, cool.
It's much clearer with an example. Okay, that's how it's going on.
Oh, good. Yeah, you mean this example here?
Yeah.
Oh, good. Yeah, okay. Yeah. Yeah, it's a lot of code to kind of go through before we actually got to running something, I'm afraid. So yeah, maybe we should have done those pushing things before like we went to pop. But anyway. Yeah, okay. I'm glad it's a bit clearer after an example. Okay, so that's the end of that bit. And so now I'm going to talk a bit about modular software. So this is kind of like a new kind of section, I guess, not very related to this concrete data structure we were building. But we are going to put our data structure into a module so that we'll see like how that plays out a bit in practice. Yeah, so what's the point of modular software? Well, the idea is that when you're making a large piece of software, you would like to combine bits and pieces written by different people. And also those different bits and pieces would probably have some like well-defined set of abstractions that has been built in that piece. And so a module is just basically a collection of bits and pieces of software which all go together, like they have related abstraction things in them, or they're trying to solve the same kind of problem. So like datastructures.jl is an example of a library which is all about like efficient data structures for holding data inside of, I guess. Yeah, and some people wrote that and put it on the internet for free. Yeah, so Julia itself comes with a whole pile of data structures and other functions. And the base library, for instance, is a module. So we can go to our REPL, which I hope that was big enough. So that's not very interesting, but the type of that. Whoa. That thing is a module. So yeah, like that thing is all of the functionality from base is automatically pulled into your own code when you go to make your write your own code, at least by default. So and a module itself will hold a bunch of different things. Like so it can hold types, it can hold constants, it can hold functions, and all those things are kind of held within a namespace so that the names that the authors gave to those things are separated from the names in your code. And that's especially useful when there's a pile of implementation details. So there's probably, yeah, there's a whole bunch of, what is going on there? Why have I only got 3 things? There's a lot of things in base. I'm not sure what's happening here. This is really weird. Yeah, and maybe that new Julia has like refused to like tab complete on things which are private. Anyway, so there's that which is probably a good thing, right? Like I'm not sure about that though. What's happening here? Anyway, there should be there's a massive pile of things in base, which are not kind of not part of the public interface. So you don't like users shouldn't be using them. Here's just a random example which I happen to be working with today, which is why I'm writing it. But yeah, there's a whole lot of things which are just internal details of how it's implemented, and they're not really meant to be used by the end users. So okay, so there's a few interesting modules, I guess we'll just okay, so yeah, like in terms of names, the module provides a namespace where there's some things which are private and internal, and there's some things which are kind of public and they should be used by everybody. And there's ways of specifying which ones those are in Julia. And like most languages will have a way of doing this. Some old bad languages don't have a way of doing this. But yeah. So yeah, the like kind of modules which come with Julia, there's one called core. Core is something you would generally not use directly, but it contains a lot of important language infrastructure stuff. So core.compiler, for instance, is got a bunch of stuff to help the Julia runtime work and compile your code. So for instance, it has type inference. Yeah, there's some type of completion stuff going on here. I'm not getting anything, so okay, so core.compiler.return type is a fun little function which is actually used by type inference. So if we wanted to know what sign the function sign would return, the type of the thing that sign would return, if we gave it a single argument, so of float 64, yeah, we could find out. And type inference says, oh, it's a float 64. What do you think would give it if I put an integer in here? Yes, it gives a float as well, because obviously you can't always produce an integer from things from calling sign on things. So that also gives us a float. What about if I put any in here? No thoughts. So type inference is allowed to give up. If you give it something and it can't figure it out, then it's just, okay, like you put any, it could be any basically. And that's kind of like a really important feature because type inference itself is, I don't think it's like kind of, it's either undecidable or like very complicated, like algorithmically complicated. I mean, like you might not be able to return a precise type for the result. So this kind of return type thing shouldn't be relied on in general. Just like type inference can't be relied on to produce like a tight result for your answer in terms of types. But it will just help the compiler out to generate efficient code. So if it can use that thing to prove there's only a float 64 returned, then you can generate efficient code. Okay, so like, yeah, lots of internal stuff lives in there. Yeah, and then there's also main, which is another one you get when just out of the box, so to speak. Now, oh, what on earth is, okay, something really weird has happened here. Might have to restart Julia. Yeah, we're restarting Julia. Sorry, yes, that is the weirdest thing I've. Sorry, what's that? Sign can give you a matrix. What would you put into sign to get a matrix out? Ah, yes, okay, yeah. Yeah, so there's like ways of defining what a function means on pretty much lots of a whole class of matrices. So yeah, like some of those will be implemented for. Oh my goodness, this is not good. I think what might have happened here. That's deeply surprising. Anyway, what I'm going to do is just not worry about them. Try and not worry about that. I'm actually not sure what's here, but happening here because I just reinstalled Julia today because I was trying to set up. Okay. Oh my gosh. So, okay, I know what's going on now. That's really bad. Not now, not now. Okay, so what's actually happened is I have a broken Julia environment where a friend's joke package is installed and it's doing terrible things to my environment. I'm so sorry. Let me see if I can get rid of it. Please work. Otherwise, I've got another Julia install, which I'm going to use in a minute once this. Okay, so to like give you some backstory for this, there's a package called what was it called? It might have just been called python.jl. And it's kind of a joke package, and there's a really funny JuliaCon talk about it from this year. So if you want to go and watch that, I recommend it. It's definitely the funniest thing that happened at JuliaCon. And it basically mixes Python and Julia together in a very, very cursed way. And unfortunately, it seems like I still have it installed on my machine, which is, yeah, a problem. I don't know how this has even happened. Okay, I don't know what's happened here. Wow. Okay. We need to get rid of this right away. So evil. Okay. Okay. So this, yeah, that package is very evil. It even installs itself into your, it used to install itself into your startup.jl. And I'm like so surprised that's still there. I convinced my friend to remove this because it's so bad. I was the first person it was demoed to. So let's get back to the lecture. It should be all gone now. Okay, good. Anyway, so like, but highly recommend watching that talk. It's very, very funny. Okay, so let's actually just do like an example of a little module. So how much time we got? We got a bit. We got plenty of time. Ooh. And actually, did everybody start using modules for their assignment for the project 2? Okay, so not everybody have. So that's good, because that means we might be doing something useful here. So here's a module. I'm just typing the module code. So basically it's a module statement, and then there's some code, and then there's an end statement. And then inside of the module, there can be functions. Whatever, f, print line high. And there could be some types. Oh. Okay, and you might also want to say what the public interface of your function, your module is. So in order to do that, we could type export f, for instance. Let's call it something longer. Just call it, we'll call it say hi, just for less namespace collision. So yeah, we could use the export statement to say that, well, say hi is a public function in my module. And if you go using my module, then you'll get say hi into your namespace and you can use it. Just like you get a whole bunch of names from base. So you get the sign function from base, for instance. So I could export say hi and also X if I wanted to. I'm just going to do that. Okay, so how do you access things within the module? So as I was saying, it's a namespace. So I might make that bigger actually. So in order to get something out of the module, you have to use my module dot. It's just like a struct. I'm pulling something out of a struct. But think of the module as like somewhat like a dynamic struct, or it can have a whole bunch of names which can be added to dynamically over time within it. So we could get the value X out. We could use say hi. And if we want to use these symbols which have been exported from here, the names, then we could go using dot my module. Now, what's that dot about? Well, my module is actually within main, and this code is being evaluated in main. So if this is just a module and it's not like a whole package, then we need to say the relative kind of path within the current module that I'm going to find my other module in. So it's just the current path dot. So I can do that, and now I could go say hi without. There you go, without actually using my module dot in front of it. Okay, so that's an example of a simple little module with some public functionality. And also you'd note that like X, for instance, this struct, I can't make one of those like this because X is not defined. So that's the reason it's not defined is because I didn't export it. So, but if I go my module.x, and I can make one of those things. Okay. Okay, we went over that. We sort of looked at how you can access things out of a module. Oh, okay. So another thing to note is that inside of this module, there's an implicit using base. So this is there by default, using base. And there's another one, in fact, there's using core. So the symbols from core and base are always available in a module by default. You can use the bare module keyword to avoid having base in there. Probably you never need to actually do that unless you're implementing some parts of the compiler or something, like myself. But yeah, if you need it and you need to have less symbols within your module for some reason, then you can actually do that. Okay. Yeah, so by default, you get everything which is base from base. And that's even like most things are defined in Julia. So if I was just to use the REPL to go 1 + 2, like where is that plus coming from? Well, it's coming from base. It's actually base.plus. Okay, so for technical reasons, we need to do that to get access to that, but that's a generic function with 189 methods. It's a whole lot. So yeah, we need to put that colon in front to get access to the operators. Okay. Oh, okay. So yes, and if we want to get something out of a package, then we can go using, and we're going to use this in a minute. So I'm just going to go using package templates. So if we want to get something from a package which is part of the package ecosystem, so in online there's about around 10,000 packages which are registered in what's called the general registry, and so that is just where everyone who writes open source code puts their code. Basically, they register their package. Well, if they want it to be public, and if they want to support it in some sense, then they put it into the general registry, and other people can use it. So like one example of that is package templates. And this is a useful little tool for making your own packages. So if you go using and then this is found within the general registry, but it's not installed yet, then we can add it to our current environment. So that's what's happening here. So this is actually a good example. I hope everybody has used the package system a bit to add stuff. Yes, good. I'm getting some nods. Oh, wow, that's a whole lot of things. So the reason what's happening here is it's busy pre-compiling everything from the project that I'm currently in, which is this courses project. And so everything that's being used in this project, in this course, at all, is being pre-compiled, which I really don't want to wait for. So we're just going to put that on the side for a moment. Okay, so that could take some time. I may have to restart it again. Normally this is helpful because it means things load quickly, but sometimes if you just want one little package, it's really unhelpful. Okay. Okay, what else we got to go through here? Okay, yeah, so the thing I was trying to get at there was that if I just open another one for the moment. Oh, whatever. So 1.10. Oh dear. Can't spell. Okay, there we go. This lecture is not going on. This is the example of why you don't reinstall Julia just before trying to give a lecture. I was going to show you some stuff in VS Code, and like it's ancient, the one I have, and I was reinstalling things. So yeah, bad idea apparently. Okay. Oh yeah, so I talked a bit about how you can navigate the module hierarchy. So modules can have other modules inside of them. And if you want to use something from the parent module, you can use those dots like I was talking about in front of. So you can go using my .my module. That means using that means one module up in the hierarchy basically, and then the current. Think of it like directories, I guess. The number of dots. Yeah, and module names, you should just use one which is kind of descriptive, and it shouldn't clash with one of the exports. So say a lot of the time you have a module which is about a particular data type. So data frames we'll see later on, I guess. And there's this data frame type. So the name of the module can't clash with the names of the types and functions inside of it. So you should choose something that doesn't clash. And the convention is to put an S. So if it's a module about the data frame type, then you call it dataframes.jl. So you'll see a lot of modules, a lot of packages, I should say, which are called have a plural on them. That's the reason. Okay, so modular max heap. How are we doing for time? We don't actually have that much left. So we'll just go quickly through this. We mostly don't need to look at the details, but we can see how you would arrange that exact example we had before, which is the max heap into a module. So one thing you can do is write this documentation. So and if you want to document some object in Julia, so modules, functions, data types, whatever, you can put a doc string in front of them, and then that will be available in the doc system. So if I go like, so if I do this kind of thing, whoops, I need to do this. So if I do that kind of thing, if I type question mark in the REPL and I look for the docs on foo, then it will show me immediately that whatever stuff I put here. In fact, if you didn't know, this is Markdown. So if I want to write some kind of stuff here, oops, it's keyboard shortcut error. Sorry, what was the question? Can you use LaTeX? Not really. So if you want to use symbols, you can. Oh well, you can use LaTeX equations. So I think I have to escape it though, because dollars means string interpolation in Julia. And yeah, so there's lots of escaping I'm going to have to do here. So if we want to integrate something, let's hope this actually works. There's a way of doing this. I've not used it for ever. So if I done it wrong, then that's the reason. Okay, no. So that's not rendered in anything fancy, but I think this is something like what you do. I mean, it has gotten a special color here, so I think it's recognized that I meant to write some LaTeX there, but yeah, if you render these documentation out with something like documented.jl, which is for generating documentation, then it should actually render this nicely rather than just as text. But I've got a limited kind of system here with the REPL, so we've still got this thing compiling over here. Oh my gosh. Yeah, it's like decided to compile CUDA and all sorts of things. So anyway, we're just going to keep ignoring it. Okay, so that's about documentation. So as I said, you can put exports. Another thing to note about this is we don't really want our type T, or we don't really want our nodes to contain strings in our in our heap data structure. We like them to contain something general, so we could parameterize it like this. So this code in this this little example here is just a bit more generalized, but other than that, it's the exact same stuff that we saw before. So like sift up, for instance, is exactly the same. So yeah, I'm not sure if there's that much we really need to talk about in all this code. I'm going to skip through it. Again, yeah, it's all the same stuff. Yeah, and there's a comment about doc strings. Yeah, so this is a more example of a more useful like doc string that you can write. But yeah, anything inside of here is Markdown. So if you want to have some actual formatting for that, it's quite easy. So you can put things in backticks that will render as code when you render out to HTML, for instance. So that's nice. Okay. Yeah, so like where should you put your modules? You don't need to put them in a single file. You could just have something like module. I don't actually have any files here that I've, that I didn't define these files, so this is not going to work, but this is allowed. So if you want to arrange your code into multiple files, you could do something like this. So you can have a main file, which just has and this is super common actually. This is a common way people lay their packages out. They'll just have a main file which has the module keyword and then a bunch of kind of maybe some scaffolding for the module, but other than that, all the implementation would potentially go in some other files. That's just like a choice you can make. So however you really want to arrange it in files, you can do whatever you want. And I would say don't, like, you can have modules. I think I mentioned that you can have modules, other modules inside your modules. So you could have this kind of, oh, that's not going to work because the include's not there, but you can have these things nested inside and have code inside of those if you want. I wouldn't go crazy with that personally. I like find it's often a case of over abstraction and separating everything out, but you can do what you want. But personally, I like to have a pretty flat namespace where most of the stuff in my package, even if it's a fairly large package, like some of the compiler ones I'm working on, it'll just be everything in there. Okay, so packages. I really wish this would finish. In fact, I can just, yeah, I can just do it in this other REPL actually. So what are packages about? So we've got modules, but those things actually we're going to have to stop real soon. So I'm going to get to, I'll just say a bit about this section maybe, and then we might have to do the creating demo next time, which I would prefer to, oh, okay. Anyway, I'm going a bit slow. So packages are a way of distributing your code. So if you want other people to be able to use it, then you need to make a package structure which has a bunch of sort of standard files laid out in a directory. So then the package manager itself, which is a library which is written in Julia, PKG, is able to kind of find so when you go pkg.add and then some package, I'm going to go outside this package environment that we have for Math 2504 so that I don't interfere with what's going on over here. Yeah, so if you go into package mode and add something like package templates, I'm going to do in the default environment. Hopefully this will just work. Yeah, okay, so that's not reasonable. Yeah, here we go again. Oh dear. So yeah, the default environment has a pile of stuff in my system. So I could start a new environment. We're at the end of the lecture anyway, so it doesn't matter, but yeah. Okay, so what's inside of a package? So let me just go to an example. Whoa, okay. Let's just go to an example package of mine. In fact, maybe we'll go to a simpler one. So this one's really simple. And this is all of it's got inside of it. So this is just a little package for, so I hope you can see that tree. That's just the directory tree that I have in this package. The only things which are required inside this package are really this main file in source/py.io in this case, because it's called py.io. So this is a little package for dealing with input and output of PLY files. So this one here is the main thing that has to have the module statement in it. So there you can see it's got some includes, and that's a pretty typical layout for things. Yeah, and then there's this project.toml and potentially a README. This is usually a good idea. So I would suggest, like, if you have a small package, just put all the documentation in the README. If you're going to write some documentation, don't worry about doing anything too fancy. So this doc directory is like where you'd normally put the docs, but you don't need to do that. And the only other thing that will really be generally in a package would be test/run tests. And yeah, so this is what is in this one. Yeah, and I have a bunch of things to say about testing, and I don't have time to say them, so I will say them next week. Okay, so I think that better be the end. Yeah, so like I did put a little note on what's it called, EdStem. If people do want to like see what I would like, I would generally use myself for setting up packages. So I did put a little note there about it. If you need to set up stuff for project 2 or anything, I would suggest using test, this standard library called test to do your testing. And it just makes your tests much easier to write, and it makes like the reports of what passed and what failed in your tests much simpler to read. So I would suggest using that. And also, if you need to scaffold your project, especially if it's more complicated, then I would suggest using package templates.jl. And it's really easy to use. It's just one line. It'll generate like this. It'll generate some structure for you like this, not with all these things, but just with like a handful of files. Yeah, and then you'll have a project that you can start editing your code in. Okay, so let's call it quits for today. Sorry, that was a little like a little disorganized. we had some slight disasters. We got through it. Yeah, you're welcome. Okay. And that's hilarious. Like that package which my friend wrote for python.jl was like, I thought I'd gotten rid of that a long time ago. It's
developing like that. Yeah, you have many environments on your computer because you have different.
Oh, it's a disaster area, yeah. Okay, I'm gonna like, yeah, I have many environments. I'm gonna quit soon before I say more. Okay, goodbye. Yes, it's Lilith, yes. So yeah, for the people online, if anyone's still in chat, go and watch python.jl, Lilith Hafner's